So we started talking about partial derivatives last time, and I think you have some homework due on it tomorrow. I think she changed all the homework dates to be on Wednesdays. Seems reasonable. So let's talk more about partial derivatives. This is Co-17C. Today is, whoa. Before I say anything about partial derivatives, just a fun fact that you don't need to know at all, but I think is super neat. Today is something called an anchor day. All these dates, 4/4, 6/6, 8/8, which is my birthday, 10/10, 12/12. My brother's birthday is 4/4, by the way. My other brother was not one of these, unfortunately. These all this year are on Tuesday. Next year, all these days, next year's a leap year. Next year, all these days are on Thursday. The year after that, they're all on Friday. Every year, all these dates are on the same day of the week, which is just kind of neat. So, like, if somebody asks you what day is Christmas on this year, we're like, well, December 12th is on a Tuesday, and 2 weeks after that is December 26th. So Christmas is on a Monday. Kind of nice. You can figure out what day stuff is on. Also, these dates as well: 9/5 and 5/9, and 11/7 and 7/11. Those are also all on a Tuesday, and Pi Day. Anyway, that's all. That's just a fun fact that I think is really interesting. Let's talk about partial derivatives now. So let's say that we have a function that's a little more complicated than the stuff well, actually, let's start off with an easy example real quick, and then we'll get more complicated real fast. So let's say we've got this function of x and y, and it's equal to x cubed times y to the fourth plus sine of 3y squared. And we want to take, so typically when I say all the partials, we usually mean the first derivatives and the second derivatives and the mixed partial. So I want to find all 6 derivatives, which, I mean, that's not the end of the story. You could say like the third derivative or the fourth derivative or the, fx, yx if you wanted to, right? You could do as many as you wanted, but we usually limit ourselves to those kind of first few. So let's find the partial with respect to x. So that's a del f del x. That del, right? It's not a d, it's a curly looking d. I encourage you to, if you want to know what it actually looks like, to Google it. Like just Google the symbol DELL to see what it looks like. But I've drawn it fairly well. You can also write this as fx. And I'm going to take the derivative of all of this with respect to x. So the derivative of x cubed is 3x squared. Leave the multiple alone. Y to the fourth is just a constant. When you multiply by a constant, that constant just hangs out. Plus, I don't see any x's there. So its derivative is 0, because the derivative of a constant is just 0. And as far as x is concerned, sine of 3y squared isn't changing as x changes. Well, we're about to for the next, yes. So if we take the partial derivative with respect to y, del f del y, or we could write it as fy, derivative of x cubed times y to the fourth. Now the x cubed is the constant that's hanging out, and the derivative of y to the fourth is 4y cubed. And now this is not a constant as far as y is concerned, right? If y changes, sine of 3y squared is also going to change. So the derivative of sine of some stuff is cosine of that same stuff, but then we have to use the chain rule and multiply by the derivative of the inside, which is exactly. And you can leave it like that. Or if you wanted to simplify it a little bit, you could write it as 4x cubed y cubed plus 6y times cosine of 3y squared. Let's find the second partials. Yeah, we've got enough. Well, we've got enough for this next one. So the second partial, del squared f del x squared, or fxx. I'm just looking at the partial with respect to x and taking the derivative of that with respect to x again. So I've got, and I should have really simplified this as just 3x squared y to the fourth. The derivative of 3x squared is going to be 6x, and the y to the fourth constant multiple is going to hang out. Not too terrible. On the other hand, fyy is going to be pretty terrible. I need a little bit more room than what I've got left on this page. Let's give ourselves a little bit more room. Come on, papers. So to find FYY, I should be very careful about where I'm at on the paper here. Or del squared F del y squared, which is FYY. I'm looking at FY and I'm gonna take the derivative of that with respect to Y. So this first part's not too bad. The 4x cubed constant multiple just hangs out, and the derivative of y cubed is 3y squared. Now over here, I've got a 6y times a cosine of 3y squared. I've got a function of y times another function of y. So I'm thinking of this as a u and a v, and I'm going to use the product rule to take the derivative of u times v. So I know that my derivative is going to be the derivative of u, which is 6 times 1. I'm not going to write the times 1, times the other part left alone. So that's my u prime times v, plus then we switch. We leave u alone, and we multiply by the derivative of v. The derivative of cosine of some stuff is negative sine of that stuff times the derivative of the inside stuff, which is 6y. And that would be my u times v prime. I feel like I saw someone about to ask a question. Did you have a question? I feel like I saw your hand like kind of wanting to raise, Maddie. Okay, cool. Are there questions about this? I will reiterate, I saw that I had a function of y multiplied by another function of y. And when you're taking the derivative of a product of two functions, we have to use the product rule. And then I don't think there's not a whole lot of need to simplify this, but if you wanted to simplify this, it would be 12x cubed y squared plus 6 cosine of 3y squared. And then 6 times 6 is, and a minus is a minus 36y squared times sine of 3y squared. I would really only bother simplifying derivatives if I was asked to, or if I knew I was going to have to take the derivative of that for a subsequent derivative, because it's definitely worth your while to make something simpler before you differentiate it. There we go. Finally, let's find the mixed partial. So I'm going to find del squared f del x del y, which is fyx, meaning we did the derivative with respect to y first, and now we're taking the derivative of that with respect to x. So I'm going to look at my derivative with respect to y, and I'm going to take the derivative of that with respect to x. I don't think you need to write this. I would say skip this stuff I'm about to write, but I'm going to write it as the derivative with respect to x of my fy, which was 4x cubed y cubed plus 6y cosine of 3y squared. I would skip this step and just say, I'm going to look at what fy is, and then ask myself, what's the derivative of that with respect to x? So the derivative of 4x cubed is going to be 12x squared. The y cubed multiple is going to hang out. And the derivative, all of this doesn't have any x in it. So the derivative of that with respect to x is going to be 0. So our answer is 12x squared y cubed. Let's find the mixed partial the other way and verify that they're the same, because they should almost always be the same. Yeah.
No. 0 to 6y constant, right?
I would say it's 0 because 6y times cosine of 3y squared is a constant. Yeah. So if we go the other direction, we try to find del squared f del y del x, which is fxy, which is the derivative with respect to y of the partial with respect to x, which was 3x squared times y to the 4th. The derivative of that's going to be, well, the 3x squared multiple just hangs out, and the derivative of y to the 4th is 4y cubed, and we get 12x squared y cubed. And to no one's surprise, these are the same as they should be. Again, I will say they're not always the same, but in this class, I can't imagine we're going to encounter any functions strange enough that these will be different. So you should always expect that the mixed partial in either order should be the same either way. Maddie. Sure, except I'm gonna say one thing. We don't say the of. So it's we just say FYY. Mm-hmm. So totally. So when I'm taking the derivative of when I'm finding FYY, which is just the derivative with respect to y of FY, I am saying, okay, I'm looking at this whole function, actually really this whole function, and taking its derivative with respect to y. So the derivative of the first part is going to be 4x cubed times 3y squared. And then for this second part, which is a product of the function 6y times the function cosine of 3y squared, I'm using the product rule. So I'm taking the derivative of 6y, which is 6, multiplying it by the other function left alone. And then I'm adding and doing the derivative in the opposite way. And then I'm leaving the 6y alone and multiplying it by the derivative of the second function. And the derivative cosine of something is negative sine of that something times the derivative of the inside something. Totally, yeah. Other questions about anything we've done here? Oh yeah, it's way down. Sorry, it's way down there. I apologize. Yeah, there we go. Where am I going papers? Over here. We're gonna do a few more examples, but other questions about this one? Let me take a quick gander at the homework assignment just to see if there's anything I want to make sure I focus on. Okay, there's some fun stuff there. All right, cool. Sure. Yeah. All right. Yeah. Okay, cool. All right. So that's terrible. Let's look at some more examples. Sure. I will also post the notes in Canvas, but you're welcome to take a photo. You're also welcome if you want to after class to like take a photo closer up if that's better for you. That's not too terrible. Again, apologies for the paper situation. Sorry. So let's look at something like this. Let's say we've got G as a function of X, Y, and Z. And we're going to say that's going to be e to the X squared divided by Z plus, I don't know, sure, tangent of Y cubed plus 5x. Fun times. And we're going to take just the first derivatives here. So we're going to find del G del X. All right. So we're just using really just using all our usual derivative rules and pretending like things that aren't X in this situation are constants. So when I look at this, I think of this as e to the X squared times Z to the negative first. That's easier for me to think of, oh, I've got e to the some constant times X squared. Or when I'm doing it with respect to Z, some constant times Z to the negative first. And we all, I hope, remember, what's the derivative of e to the X? Right, it's like the best one ever, right? Because it just doesn't change. So the derivative of e to the X, e to the X, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. That's always just the, right, when you're doing the chain rule version, you're just replacing X with the word stuff. And then in the end, multiplying by the derivative of whatever that stuff is. So the derivative of e to this stuff is going to be e to the same stuff times the derivative of that stuff, but the derivative with respect to X. So the derivative of X squared times Z to the negative first is 2X times Z to the negative first. So Z to the negative first is just a constant multiple that's hanging out. Plus the derivative tangent of some stuff is going to be secant squared of that same stuff. Excuse me. But then we have to multiply by what? Show me on your fingers, since I'm kind of deaf. Yeah, that much. We have to multiply by 5, the derivative of 5x. Or if you prefer, you have to multiply by 0 plus 5, the derivative of y cubed plus 5x with respect to x. Cool. Let's find the partial with respect to y. In fact, why don't you all find the partial with respect to y? I'll give you like a minute. Yeah, a minute. Also, for the folks on Zoom, if you have questions, feel free to, or for the one person on Zoom, feel free to type a question in the chat or unmute yourself and say words, and I will happily try to not get scared out of my skin if you unmute yourself and answer your question. I can't seem to turn up my volume, which is strange. Oh well, should be fine. All right, it's been a minute. The derivative with respect to y, b dx squared over z, 0. Right? Again, I would say that the easiest way to identify if something's a constant or not is the variable you're differentiating with respect to in that piece of it. If it's not, then it's a constant and you're done. The derivative is 0. Question? Sure. So here's what we're asking. So in fact, let's go back in time a little bit. We'll come back, don't worry. So let's say we had, I know I'm like wasting paper. Let's say our function was x cubed plus 7x plus 1. Easy function. You probably don't even need to write this down. So when I say what's f prime of x or df dx, I'm asking what the derivative is. But when we talk about the derivative of a function, what does that really even mean? So the derivative of a function says, or asks, it asks the question. The derivative asks you, how is the function changing as x is increasing? That's what this means. A derivative, really, when you think about what a derivative is, you be like, oh, it's a rate of change. It is how one thing is changing as another thing is changing. So a very common example of a derivative is velocity or speed, right? If I say, if I start walking this way, my position is changing as time moves forward. So my rate of change, or the rate of change of my position with respect to time, is positive, right? My position is increasing as time is moving forward. So if I ask, how is my position changing as time is moving forward, my position is getting larger if you're thinking like this is 0 and that is positive, or net less large than that. So here what I'm asking is, how is the function changing as x is increasing? Derivative is 3x squared plus 7. What does that even mean? Well, let's look at a particular moment in time. Let's say that x was equal to 2. Then f prime of 2 is equal to 3 times 2 squared plus 7, which is 3 times 4 plus 7, which is 19. What that means is that this function is at this moment in time, which I'm going to try and draw here, and it's going to be garbage. Just bear with me anyway. Here's my terrible drawing of this function. I regret this immediately, but it's kind of like that. It's not a good picture. Don't draw that, please. But what I want to point out is right at this moment, when x is equal to 2, what we're saying is that this function is increasing at a rate of 19 height units per 1 over unit. So the rate of change, it has a slope of 19. Every 1 over, you go 19 up. And I'm going to pretend like that's 1 and that's 19. But again, the more general idea here is we're saying, oh, how is the function changing as x is increasing? Or as whatever input is increasing. oh, well here, if x is increasing, if x increased 1, the function would increase by 19 at that exact moment. So what we're asking here, back in this other example, is, okay, how is this function changing as y increases? Right? When we're talking about the partial with respect to y. Oh, well, if y is increasing, e to the x squared over z isn't changing at all. Right? We're pretending, so I should be more explicit here. I'm asking, how is this function changing as y is increasing and every other variable is staying the same? Only y is increasing. So if we ask, how is this changing as y is increasing and nothing else is changing? Oh, well, nothing else is changing. So e to the x squared over z doesn't change. And if something doesn't change, its rate of change is 0, which means its derivative is 0. So hopefully that was a decent answer to your question, and not a fairly wordy answer to your question. That's the real reason why, because we're saying everything else is getting held stable, not changing, and the one y thing is changing, and so we're asking, oh, how is the function changing as a right? So for this one here, we were saying how we're asking the question, how is the function g changing as x increases? Oh, well, it's this again, and you'd have to actually plug in a point to have a numerical value, but generally at any particular value of x, this is how the function is changing. Well, let me write it this way. Let's say it this way. What's the derivative of e to the x? What's the derivative of e to the stuff? E to the stuff times, right. So the derivative of e to the stuff is going to be e to the stuff times the derivative of this stuff here, which is 0, exactly. Plus, now we're going to do the derivative of tangent of some other stuff. And now, since the stuff in here does have the variable y, oh, we're saying y is increasing. So the derivative tangent of something with y in it, the derivative is not just going to be 0, because tangent of whatever is not just a constant. So the derivative tangent of some stuff, just like here, the derivative tangent of something is secant squared of that something. That outer derivative part doesn't change at all. What does change is that the derivative of the inside portion now we're differentiating with respect to y. So we're going to get 3y squared, and you don't really need parentheses there, but I wrote them anyway. Or more generally, we're getting secant squared of y cubed plus 5x times the derivative with respect to y of y cubed plus 5x. That's what's happening there. Well, the answer is that, so the overall answer is this part right here. So our final answer for del g del y is secant squared of y cubed plus 5x times 3y squared. No. 0 was the derivative of just this part, but then we still had to add on the derivative of this part over here. Sorry, sorry if that was unclear from me. I apologize. Let's go ahead and find the last first partial, del g del z. So now, and this is why it's especially good to write e to the x squared over z is e to the x squared times z to the negative first, because I think it's much easier to take the derivative of z to the negative first than it is to write it as 1 over z. So again, the derivative of e to the stuff is e to the stuff times the derivative of that stuff. And the derivative of x squared times z to the negative first is going to be, the x squared is going to hang out. It's a constant. Exactly, -1, or just negative z to the negative 2. Plus, I don't see any z's there. So the derivative of tangent of y cubed plus 5x with respect to z is going to be 0. And then if for some reason you wanted to write your final answer here where you didn't have any negative powers, just sometimes something people want you to do, you could totally write this as x squared times e to the x squared over z all over z squared and put that negative sign out in front. That would be how you would write that without any negative powers. which is sometimes a requirement that people put on you so that you have to do more simplifying. Also, I will say the one thing I think that is nice about writing it this way is it's way more obvious that z equal to 0 is not in the domain of this expression. Whereas over here, it's not quite as obvious that z can't be 0. 0 to the negative 1 power is undefined, but it's easier to think of it as 1 over 0 being undefined, in my opinion. Cool. Other questions before we do more? Time is plenty of time. We should probably talk about. Let me look and see. Sorry, I looked before and I wrote myself some notes, and obviously I forgot them. It's terrible. Let me just see. Are there questions about a triple? A third. Let's do a third derivative. Yeah. I don't see any chain rule type questions that I am thinking of. I know we've done some chain rule stuff, but there's another chain rule thing that I'm talking about that I'm imagining, but I don't see any of those. Yeah. I think tangent planes and linearizations are what are coming up next.
Yeah, we did tangent plane.
Oh, okay. All right. Okay. Let me ask you all. I know this homework is due tomorrow. Are there any questions any of you have about this specific homework assignment that I could maybe do a variation on? Yeah. On this one here, the 6x root y over to minus 5 over x minus 7 or something like that. Sure, I can definitely do something like that. Let me write down something before I go with it. I'll definitely. Let me try not to get everything out of order. It's really hard to figure out what order things go in later on. God, it's terrible. Sorry, I'm missing a page. Oh well, it's right there. It's just hiding from me because it's got other writing on it. Okay, I promise. Cool. All right. Yeah, good. We're good. Well, let's look at something like f of x comma y equal to 6x times the cube root of y minus 7 over x squared y to the 4th. Yeah, that's not too terrible. So, good rule of thumb. Before you differentiate anything, it's usually in your interest to make it look simpler. Specifically, if you've got things in denominator, so I'll say more about this in a minute. If you've got stuff in the denominators that you can easily bring up to the numerator, I suggest doing it. Now, it's easy, when I say easy, as long as everything in the denominator here is multiplied together, it's really easy to bring it all up to the numerator. So I would rewrite this function as 6x times y to the 1/3 minus 7x to the negative 2nd y to the negative 4th. Technically, you can always bring up everything in the denominator if you really want to. Sometimes it's not worth it though. Just as a kind of counterexample, if you had something like f of x y equal to y cubed over x squared plus y to the 4th plus 7 to the 2nd, you could bring that up to the numerator as y cubed times x squared plus y to the 4th plus 7 all to the negative 2nd. But usually people don't when there's a bunch of addition in the denominator. It's not that you can't, it just, I don't know, and I don't even know why. It's just people usually don't. But you could. Or you use the quotient rule. Your choice. I don't want to use the quotient rule here if I don't have to. So let's find the part. Oh, let me click on this. Sorry. If you ever see the little camera thing up there, like the little side stuff, tell me because I don't like the way that looks personally. And I don't think it looks nice to you either, I imagine. Let's find del f del x. Yeah, so the derivative of 6x is 6. The y to the 1/3 is going to hang out. And I'm going to get here so you could write minus 7 times minus 2x to the negative 3rd times y to the negative 4th. But if we're thoughtful here, we can be like, oh, we're going to get minus 7 times minus 2, which is going to be plus, and then we're going to get x to the negative 3rd, and the multiple of y to the negative 4th is going to hang out. All right, you all should find del f del y. Give you a minute-ish. On your paper. Yeah, but I can make this brighter. I mean, it's not just me, right? It looks terrible. Oh, why? What are you doing? Why are you trying to shut down? Maybe it's because of this paper. No, I don't know. Yeah, I don't know what that's about. Okay, well, sometimes things look terrible. All right, del f del y is going to be a little bit less nice. But again, we're just looking at the original function and differentiating with respect to y. I'm going to not do the multiplication. I'm just going to have 6x times the derivative of y to the 1/3 is 1/3 y to the 1/3 minus 1 is negative 2/3. Over here, I'm going to write it out the long way. I've got negative 7x to the negative 2 times the derivative of y to the negative 4th is negative 4y to the negative what? Yeah. Be careful there. It is easy to go the wrong way and think, oh, 4 minus 1 is 3. But negative 4 minus 1 is not negative 3, it's negative 5, as you all correctly said. And then we should simplify. I'm going to write this using positive powers just because I can. I'm going to write this as 2x over y to the 2/3 minus times the minus is plus 28. And I'm going to write that over x squared y to the 5th. It would be just as good to write this as 2x times y to the negative 2/3 plus 28x to the negative 2nd y to the negative 5th. Either way of writing this is totally fine. Let's change gears for just a second because there were, thank you for those of you who are doing the reflections. Thank you. I appreciate it. It helps me know kind of where you're at and what you want to see. A couple people had asked about how on the quiz you would know a limit didn't exist versus not having enough information to say whether or not it existed. So let's look at something like that. And let's start with something like this. Let's say our function, and again, you'll have to bear with me because I am making something up, and making these functions up can be challenging sometimes. So if this goes awry, we'll fix it. But let's say, I think this one's going to work out. Let's say we've got something like x squared times y over x squared plus y squared. Now let's go ahead and always, and again, we're trying to find the limit, or we're trying to talk about the limit as x, y approaches 0, 0 of this function. And so let's pretend this was like the quiz, and I said, I'm going to give you two paths. I want you to try the path along the y-axis, which is really x equal to 0. So if I try this path, we're going to find the limit as y approaches 0, and we don't need to write x approaching 0 because x already is getting to be 0, of 0 squared times y over 0 squared plus y squared. 0 squared times y is just 0. So I still write the limit. And 0 squared plus y squared is y squared. And now here's where I feel like a lot of people sometimes get a little bit, I used to get confused about this a lot, actually. This limit does exist. But it's not because we're going to plug in 0 right now for y. It's because we're going to say 0 divided by y squared is what? 0, because y isn't 0. Right? It's approaching 0. Is it equal to 0? No. Limits never actually get to the point you're approaching. You get really, really close. So 0 divided by something that's not 0 is just 0. So then this is the limit as y approaches 0 of 0. But then the limit of a constant, right? Y is getting closer and closer to 0, and the function 0 is just doing its thing and being 0 the whole time. So no matter what y is doing, this limit is going to be 0. Just like, and if you feel like it'd be just like if I said my function was y equal to 5, and I said, okay, what's the limit as x approaches 3 of the function y equal to 5? Well, okay, x is getting closer and closer and closer and closer to 3. And what are the y values getting closer to? It looks like 5. It looks like they're 5 the whole time. And I wouldn't, using the word closer is probably not the best word to use here. The y values are just staying at 5. And yeah, as x is close to 3, they're still going to be 5 from either side. Same thing is true for 0. The y values are just 0 the whole time, and as x or the function values are just 0 the whole time, and as y is closer and closer to 0, the function stays at 0. And the same thing is going to happen when we try the y-axis. Sorry, the x-axis. Apologies. When we set y equal to 0, we're going to get the limit as x approaches 0 of x squared times 0 over x squared plus 0 squared. And we're going to have the limit as x approaches 0 of 0 divided by not 0. And just like before, 0 divided by not 0 is 0. And the limit as x approaches, it doesn't matter, of a constant is that constant. So let me ask you, at this juncture, could you definitively say that the limit does not exist? No, we can't say it doesn't exist because we haven't found a path that gave us a different value for the limit. There might be one. There probably is one. But we haven't done the work yet to show that there is one or there isn't one. Let me ask you a different question. At this point, can you confidently say that the limit as xy approaches 0, 0 of this function is equal to 0? Definitely not. We haven't checked. Really, you can't check enough paths. You can't exhaust our paths. We'd have to do other work to show that the limit was 0 if it was 0. And I don't actually know if this limit's equal to 0 or not. I'm pretty sure it is though. But if this were a quiz question, we would say at this juncture, there's not enough information to decide. We can't say the limit's 0, and we can't say it doesn't exist because we haven't found 2 different paths that give us 2 different values. Do you have a question?
Yeah, so basically, like y approaching 0, does it mean you plug in y or 0 for y on the bottom, right?
For this one here?
Yeah,
So we plugged in 0 for x.
yeah, but right after when it says 0 over y squared, that
I'm not plugging in 0 for y. I'm doing the division. What I'm saying from, and that's a really good question. What I'm saying from this step to this step is that 0 divided by y squared is just equal to 0. Or if you prefer, 0 divided by y squared goes into 0, 0 times y squared is 0. You subtract, your remainder is 0. So I'm just saying this is equal to that. The limit hasn't done anything yet, but now the limit of 0 is 0.
okay, and then we can't say it's 0 because we don't have enough information.
Right. Right. We haven't shown that every path has a limit that's 0. There might be a path. I don't think there is a path, but there might be a path here where the limit ends up equaling 1 or 5 or something else.
So if they're both 0, like one approaching y approaching 0 and x approaching 0, that doesn't mean that it's 0. It
Means it could be 0.
okay, and then how would we know? Like, do we ever say it does not exist?
Yeah, for sure. If we were able to find another path that goes to the origin that gave us a value that was different than the values we already found, which are 0 here, that would be enough evidence to show the limit does not exist.
Like if you plugged in like MX or something.
Right, we could try MX, although I think MX is going to be disappointing here, but we can try it. Well, let me answer other questions before we do that.
It was just like to conclude, like, so basically, if there's 2 zeros, we can say there's not enough information, but if there is a limit.
Right. If the limit was going to exist here, it would have to be 0 because we've already found one path of the limit was 0. So all the paths have to be the same for the limit to exist. And since one of them was already 0, they would all have to be 0 for the limit to be able to exist. Maddie, did you have a question too?
So on the quiz. If we try the x-axis, the y-axis, and then let's say y is the x.
Sure, but did the quiz ask you to try all those things? Because what I saw in the quiz, it only asked people to try those 2 things, and then after that, make a conclusion.
Okay, so it can stop after.
Right.
Y, x.
Right.
Right.
Right. That question was specifically asking you to try the things they asked you to try, and then based on that specific information, what can we say?
Okay.
And in this case, nothing. Now, just to kind of, oh, did you have a question too? Yeah.
So if if the limit didn't exist, it would be 0.
It would have to be 0.
But there's no way, or is there a way to like confirm that the limit does exist?
So that is challenging sometimes. So I will say that in this class, you're probably not going to be asked to do that. But here's how. Well, in fact, let's continue with this problem, and we'll do a couple things. So let's try the y equals mx, because that's a nice way to see if the limit may not exist sometimes. So if I try letting y equals mx for the limit as x, y approaches 0, 0 of x squared y over x squared plus y squared, I'm pretty sure it's still going to be 0, but let's try it anyway, because I'm pretty sure this limit exists. So we're going to get the limit as x. Oh, I didn't need to write x, y approaches 0, 0. I should have written the limit as x approaches 0 because I'm replacing all the y's with m times x. So I'm going to get x squared times mx over x squared plus mx squared. So when I write this out, that's going to be the limit as x goes to 0 of mx cubed over x squared plus m squared times x squared. And as usual, you should factor out as much x from the denominator as possible. So if we factor out an x squared from the denominator, I'm left with x squared times 1 plus m squared. And then I can cancel an x squared on the top and the bottom. You get the limit as x goes to 0 of m times x over 1 plus m squared. And that's going to give me, if I plug in 0 for x, m times 0 over 1 plus m squared, which is 0 divided by not 0, which is 0. All right, let me ask you all a question now. Is this enough evidence to say the limit is equal to 0? Definitely not. You can't check every path. The answer is always no. If the question is checking 10 more paths enough evidence, or 1,000, or literally an infinite number of paths. We are checking an infinite number of paths because m could be any value between negative infinity and infinity. And still the answer is no, that's not enough evidence to show that this limit exists. To show that this limit exists typically requires some sort of squeeze theorem argument. So here's a little point. Here's how you would show this limit exists, because I'm pretty sure it exists. I'm going to work through the argument here that I think is correct. I always start with this. X squared less than or equal to x squared plus y squared. I start with that because I have an x squared on top and an x squared plus y squared on the bottom. I know there's a y as well. I'm ignoring the y for it. Also, x squared is greater than or equal to 0. Here's my job now. Again, I don't think you're gonna have to do this. So has she done this in class at all?
Just showed it in the book, what she said. I don't think.
Right. So again, you don't really need to know how to reproduce this argument, but here's my thought process for this argument. I've got this inequality, and now my job is to try to make the middle piece of this inequality look like the thing I'm trying to take the limit of. So I'm going to divide everything by x squared plus y squared. So 0 divided by x squared plus y squared less than or equal to x squared divided by x squared plus y squared, less than or equal to x squared plus y squared divided by x squared plus y squared. Or in other words, 0 divided by not 0, less than or equal to x squared over x squared plus y squared, less than or equal to x squared plus y squared divided by x squared plus y squared is 1. Now, we still need to get a y in the numerator, so we multiply everything by y. So 0 times y less than or equal to x squared times y over x squared plus y squared, less than or equal to 1 times y. Or in other words, 0 is less than or equal to x squared plus y squared. Oops, oh my gosh, that's supposed to be in the denominator. Ah, terrible. 0 is less than or equal to x squared times y over x squared plus y squared. And that's less than or equal to y. And now we apply the squeeze theorem. So let me ask everybody, what's the limit as x, y approaches 0, 0 of 0? Right. I'm going to run out of room, which is disappointing. What's the limit as x, y approaches 0, 0 of y? Also 0. I'm gonna write this up. I'm gonna write this down here too, just so it doesn't feel like we've got a terrible page break here. Well, since this is between 0 and y, and the limit of 0 is 0, and the limit of y is 0, then the limit of the thing between those two also has to get closer and closer and closer to 0. So by the squeeze theorem, the limit as x, y approaches 0, 0 of this x squared times y over x squared plus y squared is equal to 0. Yeah.
How do we decide that?
So the thing is, I kind of knew this. I knew the way this often works is by saying that x squared is less than or equal to x squared plus something that is always not negative. Y squared is not negative. It's a very common starting place for a problem like this. Again, I wouldn't sweat it too much because you're probably not going to have to repeat it. The other thing I would say about this is what you can kind of imagine is you can imagine that the function x squared times y over x squared plus y squared is all, that's actually interesting. That's, it's interesting. This feels like I'm making things up over here. So, okay, technically there's something else I could say here. Not a big deal. But technically, when I multiplied everything by y here, I made kind of an assumption that y was positive. Because if y was negative, you'd have to change the order of the inequality. So that's true if y is positive. If y is negative, then you're going to get that 0 is bigger than or equal to x squared times y over x squared plus y squared is bigger than or equal to y. Right. What we really could have said is that the absolute value of x squared times y over x squared plus y squared is less than or equal to the absolute value of y. And then since y goes to 0, that goes to 0. So you can kind of imagine that this surface looks like something that's, well, part of it is always above the xy plane, and then it's underneath something that no matter which direction you approach the origin from, it's always going down to 0. Kind of neat. All right. Yeah, let's look at just to kind of clarify this. Oh yeah, question.
So if you go up like by yeah, right there. So you know it says limit as your mx is over 1 plus m squared. Like why do you plug in 0 in time? Because whenever you're trying to evaluate a limit, the thing that we would love to be able to do if we ever can is just substitute in that the value that x is approaching for x and the value that y is approaching for y. So since x is approaching 0, I'm just replacing x with 0. And I'm asking, when I do that, do I get a real number instead of some 0 over 0 garbage?
And here I am, I'm getting 0, right? Because m times 0 is 0, divided by something that is for sure not 0. And 0 divided by 5, 0 divided by 7, 0 divided by 1,000,000, no matter what you divide into 0, as long as it's not 0, you're gonna get 0. 1,000,000 goes into 0, 0 times. 1 plus m squared goes into 0, 0 times.
And then I have a question, like, so you know how you do like when you can plug in y equals mx?
You can always plug in y equals mx if you're going through the origin.
Okay.
That's always an option.
So to see if the limit exists.
Sure, let's do a problem. Because I think I know where we're going with this. So let's say we had something like the limit as x, y approaches 0, 0. Let me make sure I'm making up something that's gonna work. Sure. Sorry, my brain has to brain for a minute here. That'll be fine, yeah. X squared, sure. Y squared over x to the 4th plus, I might have to be careful here. Yeah, over y, 2y to the 4th. Sure, let's have fun. So sometimes it is nice to try y equal to mx. The reason this is nice is because if the limit doesn't exist, it's usually easy to see that it doesn't exist using this method. So I'm going to sub in y equal to mx. So when I do that, I'm going to have the limit as x goes to 0, x squared times mx quantity squared over x to the 4th plus 2 times mx quantity to the 4th. Simplifying, you get the limit as x goes to 0 of m squared times x squared is x to the 4th over x to the 4th plus 2 times m to the 4th times x to the 4th. I can definitely factor out an x to the 4th from the bottom. So I'm going to write this as the limit as x goes to 0 of m squared times x to the 4th over x to the 4th times 1 plus 2m squared. In this particular example here, the x to the 4th totally just cancel out. In other examples, you might have like another x left over here, and then that x goes to 0, or you might have an x here, that part goes to 0. But here we're going to get that this is equal to the limit as x approaches 0 of m squared over 1 plus 2m squared. And since there are no x's left to plug in for, that's the limit of a constant as far as x is concerned. And we just get m squared divided by 1 plus 2m squared. So let me ask you all, this is kind of a tricky question to answer. Does the limit exist? No. Why not? Well, what would it be equal to? Right, if the answer is it depends on the value of m, then it means that you could have different values for your limit, which is not okay, right? You can only ever have how many values for your limit? Only one. If you get different values, that means you're not getting the same thing every time. So just to be super extra clear, along the path y equal to 3 times x, the limit ends up being 3 squared over 1 plus 2 times 3 squared, which is 9 over 1 plus 2 times 9, which is 9 over 18. Along the path y equal to negative 2x, which is also a y equals m times x, the limit ends up being 4 on top and 1 plus 2 times 4 on the bottom, which is 4 over 9. Those are not the same. So the point is, if you get m's in your answer, and m could be any real number, I can see that picking 2 different values of m gives me 2 different values for my limit, which means the limit along this path and the limit along that path had different values, which means the limit doesn't exist. Questions? Maddie?
Yeah, in the second to third step, when we were first calculating, where did the m to the 4 come?
So oh, sorry. Sorry, that should have been m to the 4th. I'm sorry. Apologies. Good call. M to the fourth, not an M squared. Sorry about that. Doesn't change much, but it does change our values here. So that should have been a 1 plus. Sorry, so if M is 3, I get 1 plus 2 times 3 to the fourth, which is 1 plus 2 times 81, which is 162. So that's 9 over 163. And over here, if you plugged in -2, you'd have 4 over 1 plus 2 times 16, which would be 4 over 17. Oh, sorry, 4 over 33. Sorry, it's terrible, I know. But the point really is not that you shouldn't actually plug in values like I did here. You should be like, oh yeah, if I'm getting M in my answer, and M can be anything, that means different values of M produce different limits, which means different limits means the limit doesn't exist. So for this kind of problem in the quiz, once you got an M in your answer, like, oh, the limit doesn't exist because M can be anything.
Overall. Like if you have like a quiz or like on the homework or something, most of the time we can assume that like if we had a problem like that, it would be either it doesn't exist or we don't have it.
Right, because I don't think she's asking you. So I should say, let's back it up. Before any of that, we should back up and say, if you started off by plugging in what X and Y were approaching and got what? 0 over 0, then what you're saying is 100% true. You can generally make a fairly decent assumption that either the limit's not going to exist when you have a 0 over 0 time, or since we probably aren't going to show that the limit exists, we're not going to have enough evidence to say whether or not it exists. But yeah, but you should always start by checking that if when you plug it in, you actually get 0 over 0. Because if you just get like 5 over 2, that's your answer.
So 0 over 0.
No. 0 over 0 is do more work. 0 over 0 is try some paths. And if you get different values, limit doesn't exist. And on the quiz, it's if all the paths give you the same results and they're not asking you to do anything else, you don't have enough evidence to say whether or not it exists. Because as far as you know, it could exist, or there's a path we haven't tried yet. It's not. Sorry, what's your name again?
Ramen.
Ramanan?
Yeah, ramen.
Ramen.
Yeah.
Okay, cool.
So, you like, is there a way where you plug in X equals Y squared? And then, or like you compare that limit to, or the answer you get to that, from that to Y equals MX?
You can so the thing is here we wouldn't need to do that here. Because so here Y equals MX gives you the same value. Sorry, a different value for different values. Let's look at a different example. Let's say I had. Let me make sure I make up something here that okay. I mean, let me think for a second here. Let's say we have the limit is X comma Y approaches 0, 0. Let me be careful here. Sure, let's try. Excuse me. Let me think for a second here. Sorry, one sec. That should be fine. Let's try this. Sure, let's try 2xy over x squared plus, that's not right, James. X cubed plus, oh, brain. Sorry, I was trying to make something that's going to work here. I don't know if I love this, but we'll try it. Not thrilled about this choice, but that's what I've got. So let's look, let's say we were trying to be general. I'm thinking like, well, maybe Y equals MX is a good thing to try. I personally would always start off with Y equals 0, X equals 0. And I can, interesting. So I can certainly see here that Y equals 0 would give me 0. Because if I plug in 0 for Y, I get 0 on top, X cubed plus 0 on the bottom. X equals 0 actually doesn't help me. So if I plug in 0 for X, I get 0 over 0 plus 0. So I'm going to avoid that for now. Because it's still 0 over 0, I don't really know. So let's try the more general Y equals any line through the origin. So if I do that, I'm going to get the limit as X goes to 0 of 2 times X times MX over x cubed plus 3 times x times mx squared. Nope, not squared. Why am I squaring that? I'm thinking ahead. That's the problem. There's no reason to square that. I'm just plugging in mx for y. Let's see what happens here. With the limit, this x goes to 0 of 2mx squared over x cubed plus 3mx squared. I factor out an x squared from the bottom. And I'm left with an x plus 3m. X squareds cancel. So I get the limit as x goes to 0 of 2m over x plus 3m. Right? Now what do I do? Now what do I do? Right. So if I sub in 0 for x, I get 2m over 3m, and 2 times m divided by 3 times m simplifies to just. So no matter what line you go through that goes to the origin, the limit is always 2/3. So the limit might be 2/3, or there might be a path that gets to a different value that shows it doesn't mean this. Right. Interesting here. I will point out that we already know what makes it not exist. I already said it. It was the line y equal to 0. Right, because y equal to 0, you might think that should also give you 2/3, but that's really a 0 over 0. So that ends up being a different value, which is indeterminate. Well, let's check something else just for fun. Let's say we missed that because sometimes it's easy to forget about that one. Let's try, and I think this should work. We'll see. Maybe it won't work. Let's try y equal to x squared. I designed this one so that hopefully that would work, but we'll find out. So doing that, I'm going to get the limit as x goes to 0 of 2 times x squared over x cubed plus 3 times x squared. That's going to end up being the limit as x goes to 0 of 2x cubed over x cubed plus 3x cubed is 4x cubed. The x cubes cancel. You've got the limit as x goes to 0 of 2/4, which is just 2/4, which reduces to 1/2. And those limits are not the same, which means the overall limit does not exist. Yeah.
So in general, like, when are you supposed to do something? When, like, you get like 2/3?
So personally, I usually don't do this. If I'm trying to see if a limit exists or not, I usually try x equals 0 and or y equals 0. Then I try y equals x. Maybe I try y equals 2x or 3x. But if those seem like they're going to keep being the same, then I move on to higher powers. I try something like y equals x squared, or x equals y squared, or y equals x cubed, or x equals y cubed. But there's really no like set process every time. It's kind of like we try stuff until it seems like we're trying something that seems reasonable. But it's not just to do this, then this, then this, and this, and this. It's a look and see what you kind of got. I picked x squared here because I was like, oh, if I plug in x squared, I can see the power of, and I designed it already thinking I was going to let y equals x squared. But I was like, oh, I know if I let y equals x squared, I'm going to get the highest power of x cubed on the top and the highest power of x cubed on the bottom. That's going to work out for me. If I had tried y equal x to the third, it wouldn't have been so great. I mean, it might have been fine, but if I did y equals x cubed, I would have had the limit. Can you see that? Yeah, you can see that. As x, y goes to 0, 0 of, sorry, 2 times x cubed is 2x to the 4th. X cubed, and you're going to get a 3. X times y cubed is x to the 4th. And if you factor out an x cubed, that's going to end up being 0. Which I suppose is helpful compared to 2/3, but often 0 is something you've already gotten many times. So it really kind of just depends. Excuse me. Other questions about this? I know the limits are a little bit daunting, but they're really, really not too terrible.
I noticed in the photo they focus on like one limit, the positive x and y.
Mhm. Yes, let me take a look, because I assume yes. Let me take a look and see one of those kinds of questions. Oh, I don't think that's. Let me see if I can do this quickly here. Sorry, I know that's not this assignment though. Oh my gosh, always in the way. Let's go back to assignments. You know if that was 9.2 or 9.1? Probably 9.2 or 10.2, but I don't know why they're mislabeled like this, but whatever. Let's take a quick look. Let's go ahead and do that again. Generate the hard copy. So let's see here. Oh yeah, like this one here. Yeah, I don't know why you would specify the positive x-axis. I don't think there's any really good reason. I will say that if they are specifying, so like for example, and let me just write this down here. If my function it might just be a test of your ability to know what that means. So if I said I wanted to find the limit along the positive y-axis. Okay, so here's my positive y-axis. So if we're on the y-axis, then x is equal to 0. Okay, great. So here's what I think and again, web work won't show this. Like the work you should do, someone asked you this on a test. Here's the nuance I think they might be looking for. I don't know if they're actually looking for this, but they might be. We should be taking the limit, and I'm going to leave off the approaching part here for a second, of 4 times 0 squared minus 7y squared over 0 squared plus y squared. And we're doing the limit as y approaches 0 from the right or from the positive side, right? Because if you're on the positive y-axis, then y is positive, and you're approaching 0 from the being larger than 0 side. So in my mind, this is the only thing that is different about that. The math doesn't change. Now, here's a better reason why you might actually need to do this. And by the way, so here you get the limit as y goes to 0 of negative 7y squared over y squared. The y squared would cancel, and you would just get negative 7. Sorry. There's no good reason to do this here, in my opinion. But if someone said your function was something like, and I'm going to make something up that probably doesn't have a limit or that has a limit that's hard to figure out. If someone said the x plus y over the square root of x plus the square root of y, and I wanted to find the limit as x, y approaches 0, 0. Well, now it should be noted that x is not allowed to be negative. Y is not allowed to be negative. You can't take the square root of a negative number. So here, taking the limit along the positive y-axis really makes a lot of sense, because we're saying, oh yeah, y has to be positive because of the domain of this function, right? The domain of this function is everything in the first quadrant except for the origin. But you've got the entire x-axis and the entire y-axis, and everything where x and y are positive. They just both can't be 0 at the same time. But you can't come at this thing from anything that's in the second quadrant or the third quadrant or the fourth quadrant, because neither x nor y is allowed to be negative. So you could say, yeah, along the positive y-axis, we're going to do the limit as y goes to 0 from the right of 0 plus y over 0 plus the square root of y. And then that's the limit as y approaches 0. Y divided by the square root of y, which is just the limit as y goes to 0 from the right y divided by the square root of y is the square root of y. And then you can plug in 0 and get the square root of 0, which is 0. So along that path, the limit is 0. Along another path, the limit's going to be 0. I don't know what the limit actually is. It might be 0, but we don't have enough evidence to make a conclusion based on knowing these two paths, or one path gives us 0.